Hello again. We are in the second day of our quarantine, going through projectile motion. Unfortunately, we just lost the video that we did during the live stream, so this one will not be live. We're looking to find the slope of an arc of a ballistic object, find velocity vectors, create equations for trajectories, and determine the angle at which a ballistic object should be launched to reach a set height at a set time. So the first thing I'm going to do is I'm going to go through all of the stuff that we've already covered with projectile motion right before the break. So just to review, we have scalar and vector quantities. Scalar quantities do not have direction, so this is without direction. Vectors are with direction. So what that means is, if I told you that this was 4 meters, that would be scalar. If I told you that this is 4 meters west, that would be displacement. So if it has direction, it's a vector. If it does not, it's scalar. For all of the values on this chart, we could derive in terms of time in order to work our way down. So if I have a function for displacement and you derive it in terms of time, I will end up with velocity. If you have a velocity equation and you derive it in terms of time, you'll end up with acceleration. Last week, we started with some sort of a vector. That vector had both a magnitude, v, and a direction, theta, an angle. If I wanted to find the horizontal velocity, so that's the horizontal component of that vector, then I could solve for it using cosine. The cosine of our angle is equal to adjacent, vx over v. Cosine angle equals vx over v. So I can multiply both sides by v in order to solve for vx, to get vx equals v cosine theta. Do the same thing for y, setting up a sine equation. So here's my opposite over hypotenuse. If I do opposite over hypotenuse for that velocity vector, I'll end up with my sine function. Multiply both sides by v, and I've got my vy, so my vertical component of that velocity vector. So that's both my initial horizontal velocity and initial vertical velocity, which we can then use to set up our vertical distance and horizontal distance equations. So taking this vx, I can substitute into my horizontal speed and multiply times time in order to get my horizontal distance. We can do that because gravity does not act left or right, it only acts up or down, so we don't have to worry about any acceleration due to gravity, and we're not starting with any extra horizontal distance. For my vertical distance, though, I do need to worry about how high we were when the object was thrown, and the acceleration due to gravity. So as we worked out 3 or 4 class periods ago, that would give us half of the acceleration due to gravity times time squared once we worked backwards with our acceleration. Our initial velocity times time and our initial height. Okay, so with that, in previous classes we did one of 3 things. So we were either finding maximum height when an object hit the ground or when an object had its maximum horizontal displacement. For instance, in this problem that we had a couple class periods ago where Mick was jumping off a diving board, she was jumping from an initial height of 29.4, initial height, so that's 29.4 meters, initial velocity of 9.8 meters per second, initial velocity of 9.8 meters per second, velocity of 9.8 meters per second, at a 30-degree angle. So here's my 30-degree angle here. Again, we can use that to solve for our vertical velocity and horizontal velocity. And then plug those into our equations to get, this is 1/2 of negative 9.8 is negative 4.9 t squared, plus my vertical velocity, which we solved for as 4.9 here, plus our vertical height. Okay, we do the same thing for our horizontal displacement. Our horizontal velocity was here, 4.9 root 3, times time should give me my horizontal displacement, or how far away we are horizontally from the diving board. Okay, so with these 2 equations, we can find our position. How far above the ground am I, and how far away from the diving board am I? If I want to find the maximum height, because our object will start going up and then start coming down, so my velocity is positive as I am going up, so from here to here, but then my velocity is negative as I start going down. There has to be a point where our velocity equals 0. So I'm going to derive this vertical displacement equation to get a vertical speed equation. So that's my vertical velocity. Set that equal to 0, and then solve for the time. If I do, I get half a second. If I want to figure out how high the object went, then I can take that time and plug it into my vertical displacement equation to get how high we are in meters at half a second after Mick jumped off the diving board. In this case, 30.625 meters. If I want to know when the object hit the ground, when an object hits the ground, its height will be 0, so I can set this vertical displacement equal to 0. And solve for time. Right now, everything can be divisible by 4.9. So if I divide all of this by 4.9, I'm going to divide by negative 4.9. That way I've got a positive number in front. Divide by negative 4.9, divide by negative 4.9. 29.4 divided by negative 4.9 is negative 6. 4.9 divided by negative 4.9 is negative 1. Negative 4.9 divided by negative 4.9 is 1. So I've got this, which does factor. T minus 3, t plus 2 equals 0. Therefore, t is 2 or negative 3. We know that negative 3 seconds doesn't make sense for us in real life, so I can get rid of that one. That would have been 3 seconds before we threw the ball. So that tells us which one we're going to use. Okay, so that's when the object left the ground. If I want to find the maximum horizontal displacement, I can then take that time, plug it into our horizontal displacement equation, so that's here. If I plug 2 into this equation, I'll end up with 2 times 4.9, which is 9.8, times our root 3 is 9.8 root 3 meters, which if we multiply out is 16.97 meters. That's how far away Mick will end up away from the diving board if she jumps. Okay, if I want to find the slope of an arc, that's the slope of our, if I was going to graph this, height at any distance away from the diving board in meters. This slope would then be rise over run, or your change in height over your change in displacement from the diving board is just dy dx. If I want to find that using our horizontal and vertical velocity components, we can do that. My change in y over time divided by my change in x over time means that my 1 over dt will cancel, leaving us with just dy over dx. Okay, here it is again. So using our example from the last slide with Mick, we had one equation for height at any time and one equation for displacement away from the diving board at any time in meters. If we derive those, my derivative of our height equation will give me my vertical velocity. So this is my vertical velocity at any time. My derivative of my displacement equation, this is horizontal displacement, will tell me my speed. So this is how fast we're going horizontally at any time, or horizontal velocity. So once I've got both of those, I can take my dy over dt, so that's my derivative of my height at any time, and my dx over dt is my derivative of my horizontal displacement at any time, is my vertical velocity divided by horizontal velocity. It gives me my change in y over change in x, because my change in times will cancel, or this equation. So I can plug in any t you want. So if t is 0, then you can see I would end up with a positive number. If t is 0, my slope of this graph is positive. But if t is bigger than 1/2, then I will end up having more negatives on top. So my sign total will be negative. After we pass that halfway point, which we said happened at t equals 1/2 of a second, our slope will be negative. Okay, we can also solve for time in order to get rid of time in our equations. So if I wanted an equation to graph y in terms of x, that's like the shape of the trajectory that the ball or the object, or in this case Mick was traveling as she jumped off the diving board. So I would need an equation y in terms of x instead of y in terms of time. So I'm going to take this equation for x and solve for time. If I do, I can divide both sides by 4.9 root 3 and get one equation for time. Okay, then I can take this time and plug this time into our vertical displacement equation. So that'll give us the height at this specific time. Okay, if I plug in this time, then what we'll be left with is our height at that time, or y. Since we do have a variable in here of x, you could input any x you want, and that would give you your height at that distance away from the diving board, which is what we want. Graphing that function, so putting all of those points together, will give you the parabola that tracks Mick as she jumps off the diving board and then lands in the water. Okay, so going through this, we're going to take this time, plug it in. If I square this, this will be x squared on top, 4.9 squared on bottom. One of these 4.9s will cancel with one of the other ones, leaving only one 4.9 on bottom. Root 3 squared will give me 3. Okay, this 4.9 and this 4.9 will cancel, leaving me with x root 3 here. So if I simplify, I can multiply this by root 3 over root 3 to rationalize, to get rid of that square root on the bottom. Gives me x root 3 over 3. For this term, 3 times 4.9 is 14.7, so I've got negative x squared over 14.7 plus x root 3 over 3 plus 29.4. The parabola that tracks how high I am at any distance in meters away from the diving board horizontally. Okay, one more thing we can do is solve for an angle. So if I want to find the specific angle that I would need in order to land 50 meters away, if we were launching at 100 meters per second, for example, we can do that. So what we're going to do to find out what angle you need to land a certain distance away is we'll take our distance equation. So we know that we're supposed to land 50 meters away. 50 meters away. And we've got a general form for our horizontal displacement is my horizontal velocity times time. So we can also solve for that. I know our object was launched at 100 meters per second, 100 meters per second. So if I want to solve for the horizontal velocity, we can use our cosine of our angle is equal to our horizontal velocity divided by our total velocity. Therefore, Vx is 100 cosine theta. Doing the same thing for our vertical velocity. We can solve for Vy to get this. Okay, so my 100 cosine theta is my horizontal velocity, and I can take that 100 cosine theta and plug that into our horizontal velocity here. So that's 100 cosine theta. Okay, now I've got two equations for the horizontal displacement, 50 and Vxt, so I can set those two equal to each other and solve for time. So if I divide both sides by 100 cosine t, I'll get 100 cosine theta. I'll get t is equal to 50 divided by 100 cosine theta. Okay, I can also use my vertical displacement equation to solve for time. So if I do, when the object hits the ground, our height will be 0. So I'm going to set my height equal to 0. And use our vertical displacement equation, which needs our vertical velocity, which we found here. So I'm going to plug in our vertical velocity. Okay, now that we've got our vertical velocity, I can factor out a time from both of these. If I pull out one time from both of these, I'll end up with our next line, which is t times negative 4.9t plus 100 sine theta. So t is either 0, which is when the object was on the ground initially, no time had passed, Or if I solve this part, I can move negative 4.9 to the other side and then divide by 4.9 to get t equals 100 sine theta over 4.9. So now I've got two times that I know should be equal to each other. These are both the times when the object lands, so I can set them equal to each other and solve for our angle. Okay, so our first time, 50 over 100 cosine theta here. And our second time that we got with our vertical equation goes here. Okay, so now I'm just simplifying this. 50 divided by 100 is 1/2. I can multiply by the cosine on both sides, and that gives me this line. Okay, then I'm going to multiply by 4.9 and divide by 100 on both sides, so that'll get rid of this and leave me with 4.9 over 200 is sine theta cosine theta. I don't want you to solve this one by hand. Instead, I want you to plug this into a graphing calculator or Desmos. If you do, so here's sine theta, cosine theta, and then y equals 4.9 over 200, and we can find the intersects. If you're on Desmos, make sure that you are in degrees, not radians. If you're on a graphing calculator, also make sure you're in degrees, but you can hit y equals, graph y1 is sine x cosine x, y2 is 4.9 over 200, hit graph, and then calculate your intersects. So that's second, calculate intersect. Okay, so that gave us, our angle was 1.4 or 88.6 degrees. Last thing, if I want to solve for the total velocity vector, we can do that. So our total velocity vector is how fast we're going total at any time on the arc. So what we can do is we can take our instantaneous horizontal velocities. That's how fast we're traveling horizontally right now, which is a derivative. So that's my x prime of t is my derivative of my horizontal displacement is my horizontal velocity in terms of time. I can do the same thing for my vertical velocity. If I take my vertical displacement equation, my height, and derive that in terms of time, you'll get your instantaneous vertical velocities. That's how fast you're traveling up or down right now. Once you know how fast you're traveling left or right now, and how fast you're traveling up or down right now, we can use Pythagorean's theorem to figure out the magnitude of how fast you're traveling total right now. So my total speed is just Pythagorean's theorem and solve for v. If I want to get the direction, I can use tangent. The tangent of my angle would be equal to my opposite divided by my adjacent. If you solve for the angle, we could say our angle then is equal to the arctangent of your vertical velocity right now divided by your horizontal velocity right now. And that will work for any time on the arc. Okay, so that's it for the new stuff. As far as homework goes, on Wednesday at 9 a.m., we have the homework from the last session due. So that's weight and tension. On Friday at 9 a.m., we have the projectile motion, challenge problems due. For the challenge problems, there are 6 problems on that sheet. I worked out 3 of them because I know that this is a little bit more difficult and we're in a setting where you can't really ask questions when you're in the moment. However, you can hit me up on WeChat if you have questions on any of the homework stuff. The other 3 questions are not solved. They are long form and should take you about an hour or so if you're working at about an average pace, I think. If you really know what you're doing, it'll be a little bit shorter than that. If you have to look stuff up, it might take a little bit longer. Okay, now several of you did have questions on the weight and tension from the first homework, specifically on the last problem. And I'm kind of in agreement with you that I don't think I gave enough information during the live lesson to solve the last problem. So I'm going to go through parts A and B, and then I'm going to ask that you guys go through parts C and D on your own. So this is our homework. We were given that there are 2 masses attached by a string. The mass on the table is 10 kilograms. The mass hanging off the table is 20 kilograms. So the first thing we need to do is, if there is no friction, figure out what the total amount of acceleration is. So using our general equation, F equals ma, I can solve for the total accelerations. That means the sum of my forces, so this is a sigma sign, it just means sum. So if I add all of my forces together, I should get all of my masses added together times my acceleration total. My acceleration total is the same for both of these objects because we are connected by the string. So whatever the acceleration of mass 1 is going to be the same as mass 2 because we are considering the pulley to be massless, and we're not considering rotational inertia for those of you who are in physics. If you don't know what that means, don't worry about it. It just means that the acceleration of both of these blocks will be the same. Okay, so if that's true, then we can say F equals ma, so I can divide by m on both sides to solve for a. So that gives me my acceleration is equal to the sum of my forces divided by the sum of my masses. The sum of my forces would be, so for my 10 kilogram mass, I do not have any forces acting up or down. So the sum of my masses is 0. Or sum of my forces is 0. For my second mass, I do have a force that's acting up or down, so that's the force of gravity, which is 9.8. So my total acceleration then is going to be 2/3 of 9.8, or 6.53 meters per second squared. Okay, so then once I've got that acceleration, if I want to figure out what the tension in the rope is, I can do this one of two ways. So I can either look at the hanging mass. So if I just look at the hanging mass alone, I have two forces acting on that hanging mass, the force of gravity and the force of tension in the string. So the force of gravity minus the force of tension should give me the total force, which is my mass times acceleration. So that gives us our equation here. Gravity minus tension should give me my total mass times acceleration. Okay, in this case, my force of gravity is 9.8 meters per second pulling down. My mass is 20 kilograms. My tension is acting opposite to that, so my sign is different. So I've given this a negative sign. That was confusing to some people in the live session, so I'm going to backtrack really quick. I called going right positive and going left negative. I know that is a little bit unusual because that does mean that down is positive right now. But if you look at the other mass, if I made this negative, that would be okay, but for my other mass, negative would have to be going to the right, which is unusual as well. So it doesn't matter which way you choose, but you have to be consistent as you go through. So if you say the right is positive, then down has to be positive as well, because both of these masses are moving together. If you say left is negative, then this up is negative. If you change that and you said down was negative, then to the right here would also have to be negative and to the left would be positive, because they would have to be acting in opposition to each other. Okay, so going back to this one, if I'm looking just at the hanging mass, only at the hanging mass, my hanging mass is 20 kilograms. I've got a force of gravity here, 9.8 times 20, minus my force of tension should be equal to my total force. So that's 20 kilograms times my net acceleration, 2/3, 9.8. And if we solve for tension, I get 65.3 newtons. Interestingly, and this should work because my blocks are connected, and our pulley doesn't have any mass or rotational inertia. If I just looked at the other mass, the 10 kilogram mass, there is no force of friction in this problem, which means the only force acting on this block is the force of tension. Therefore, tension is equal to my mass times acceleration. And if you solve that, gives us the exact same answer with our 10 kilograms. 10 times 2/3, 9.8 is also 65.3 newtons. So I've got the same tension in the line on this side as I do on this side. Okay, thank you very much. I'm sorry we weren't able to get the live stream video working this time. I will see if I can fix that for next time, and I will see you guys on Thursday for the next live session. Thank you.